Alright, hello everybody. I'm going to be presenting lab report 1 for our physics 20 to 11 class. And the first lab is around constant velocity. Our introduction is simple. We want to observe an object traveling in constant velocity. We want to observe Newton's second law of motion, which is occurring in our object. We also want to compare the motion with a computational model. Our key assumptions are as follows. We have no resistances of any kind. This includes friction, air resistance, material resistance, etc. So the net force on the object is actually 0 newtons. Flat surface, so there's no form of acceleration or deceleration on the object, and the object also travels in a continuous straight line. Our main laws are as follows. We have Newton's first law, which states that an object will remain at rest or in motion at a constant speed unless an external force acts upon it, and Newton's second law, which states that the force applied to an object is equal to the object's mass multiplied by its acceleration. The formulae involved are as follows. We have the position update formula, which is Rf is equal to Ri plus V average delta t, and the velocity update formula, which is Vt is equal to V naught plus At. If we go to our setup, the mini experiment consists of the following. We have our system, which is the object, in this case being a battery, and the surroundings being a scale for measurement behind the battery and a whiteboard for visual clarity. Our initial conditions are a position being negative 0.292 meters and time being 0 seconds. So the negative 0.292 meters is because of the tracker, by the way. And if we go into our methodology, the experiment was produced in real life and the data was analyzed using tracker. The model was produced online via GlowScript and was verified as well. And the readings from the experiment and the GlowScript actually match for the most extent other than few friction-based errors. So now we go to our original video. It's as follows. So that's our original video. You can hear my teammates. We're all talking in the background, discussing this may be the attempt. And this is the GlowScript one, the tracker one, my bad. As you can see, we have the red line following the battery, which is our auto tracker, and we have the blue line, which is our calibration stick. So now, regarding our tracker data, this is the actual graph I exported via tracker. We can see our initial position as follows. We have our initial velocity, which is delta r divided by delta t. And when we calculate it all out in a calculator, we get 0.181818 meters per second. So our overall velocity, when we include the y vector, is 0.181818, 0 meters per second for the x and y vector. If we go to our GlowScripts code, we have our mass, we have our position and velocity, which I updated as follows compared to my code and the tracker. We also have delta t, which I also extracted from tracker. Then if we go to our actual loop, we have while t less than 2.4. 2.4 is the final time in the actual tracker. Then, as you can see, F net is 0 because there's no force acting on the object. We have our velocity and position update formulas, and we have our plotting. So for this one, we can see it's actually, I've taken a video of our actual graph. So this is via GlowScript. I just took a video of it. It looks quite accurate and resembles the actual tracker. And if we look at a tracker via GlowScript graphs, they match for the most extent. There is some issues in the data here if you compare above the x-axis, but that is primarily due to friction and other forces acting on the actual object, which is not being accounted for in GlowScript. Now if we go to our minor errors in the reality data, we have the human error when we actually twirl the battery on the actual surface. There's some force being applied by us. There are also outside forces such as friction and air resistance, which also slow down the object. There may be also computational errors such as tracker-based related to calibration and the auto-tracking feature. So these are just a wide variety of errors that could have impacted our entire experiment. And now we get to the question if the x-axis was flipped. So we would have the same graph, only thing it would be inverted. We'd have a negative slope instead of a positive one. Our magnitude for the rate of change would be same. And it would just look like our battery is moving backwards instead of forwards. And what does this project mean when we think of the net force acting on the battery? We cannot determine the net force due to various forces acting on like gravity, air resistance, friction. And it is very challenging to achieve similar forces on a model. Hence, whenever we do an actual experiment in real life, there will always be certain forces acting on it. If we go to our conclusions, we have from our analysis, we very likely have a matching data from our tracker and GlowScript. And the conversion actually works when we try to go from observing the Newton's second law to actually computing it in a computational model. So that's pretty much all I got for our first experiment in lab 1. Thank you all so much.